Hello everyone. In this presentation, we will explore OpenGL's polygon fill area functions, focusing on how to use them effectively for creating various polygon shapes. So let's get started. Polygon fill area is a closed shape in computer graphics with color, pattern, or texture. It is used for rendering objects, UI elements, and game environments. In this session, the key concepts we'll be focusing are on the vertices of the polygon, edges, and the color which we're gonna fill inside the polygon. Polygons are generally classified in two types. One is convex and concave polygons. Convex polygons, uh, all the interior angles in convex polygons are less than 180 degrees. Any line segment between 2 points in the polygon lies entirely inside the polygon. So every angle made inside the polygon is always less than 180. It's very easy to fill using simple algorithms. Whereas in concave polygons, at least one of the interior angle is more than 180 degrees. As you can see here, the angle is more than 180 degrees. It's more complex to fill and often require decomposition into convex parts. Uh, inside out, inside outside test. So various graphic processors often need to identify interior regions of objects. Identifying the interior of a simple object, such as convex polygon, a circle, a sphere, is generally straightforward, but sometimes we must deal with complex objects. For that, we use these tests. So identifying the regions of the object is crucial in various graphic processes. Simple objects are easy, as I said before. For complex objects, which have many intersecting edges, require more advanced methods. So as you can see in these figures, it's hard to figure out which one is the exterior, which one should be included or not included. So there are two main algorithms tests for this. One is odd even rule and non-widening number rule. Odd even rule. Odd even rule, also known as the odd parity rule or odd even rule, is a method for determining the interior of a polygon. So let's get into the process. Draw a conceptual line from any point P to a distance point outside the polygon. Count the number of times this line intersects the edges of the polygon. Odd number of intersections, point P inside the polygon. Even number of point P outside the polygon. So applications of this useful for filling complex regions such as area between intersecting shapes like uh, concentric circles or polygons. Non-widening number rule. This rule determines the interior of the polygon by counting how many times the boundary winds around the point P in a counterclock direction. So it's like not same as the audio even, but it's kind of different. So in this process, we'll initialize the widening number to 0. We'll draw a line from point P to a distance point outside the polygon. For each edge crossing, we'll add a number to the widening number for right to left crossings and subtract one from the widening number from left to right crossings. A non-zero widening number, point P inside the polygon, and zero widening number is point P outside the polygon. Yeah. Applications of non-widening number rule are provides more versatile method for identifying interior points, especially complex shapes, can handle shapes where odd even rule might fail, offering a different perspective on interior and exterior regions. Now let's discuss about OpenGL polygon fill area functions. OpenGL procedures for specifying fill polygons are similar to those of points and polylines. Using GL vertex functions, we can input the coordinates for the polygon vertex. For any vertex, like we use the GL vertex function and specify the coordinates in it. I'll be showing it through example further. Complete polygon is described with the vertex list placed between GL begin and GL end. So GL begin specifies the start of any polygon or a shape which we are going to create, and GL ends uh, ends the polygon basically. Specifying polygon fill areas. Use GL begin and GL polygon. GL polygon, we are using it for creating polygons, like the minimum number of vertexes are three and maximum can be anything. So we'll be starting with GL begin and in brackets GL polygon and GL end to specify the polygon fill areas. An example for convex polygon with six vertices is mentioned below. So as we can see here, GL vertex 2 is basically the number of coordinates and I is the integer and V is the vectors. And we actually have given the P1, P2 points earlier, which we are just using it now. So as you can see, by just using this function called GL polygon, we can add many vertexes like we need. So like P1, if we have n number of points, all the points would be connected to like continuously. So as I said, at least three vertices are required, otherwise nothing is displayed. Now using GL triangles, we can specify individual triangles. So here, like since we are mentioning around six vertices, but we can only see two triangles which are separated. So this is because it's a triangle and it has three sides. So it will pair up the number of it will only choose 3 points. So P1, P2, and P6 is being chosen here, and P3, P4, and P5. If you mention two more points like P7 and P8, that would create a separate triangle, or no, it wouldn't create a triangle because it doesn't have another point. So again here, at least three vertices are required, and if the number is not a multiple of three, a triangle is not created. Yeah, like I said, if we are using P7 and P8, it's ignored. Uh, Now we'll use a GL triangle strip to specify strip connected triangles. Example, a strip with six vertices. So as we can see, it's same as the first polygon, but here each and every like the polygon is basically made up of four triangles. So it splits into like 1, 2, and 6 is a triangle. Then it will go from 2, 6, and 3. Then 6, 3, 5. Then comes 3, 5, 6. Sorry, 3, 5, 4. So at least three vertices required. That's the same for every polygon we're gonna create. And the number of vertices, if the number of vertices are n, the produced triangles are n minus 2. If there are eight vertices, we would be getting six triangles. So this is in this we are connecting the triangles concurrently, like 1, 2, 6. Next would be 2, 6, 3. Then 6, 3, 5. Uh, the same goes on. Next we use GL begin triangle fan. So this is to specify triangles sharing a common vertex. So here the first point is P1. So each and every triangle that's gonna be created here will share the same vertex, which is P1. So it's all here also it's we give n vertices, we are gonna get n minus 2 triangles. So it's same as the previous one, but all the points like all of them are sharing a common vertex, which is P1.